So let us solve this problem here. So you have two identical metallic spheres A and B. Now these two are identical and then they have similar charges, say plus Q on both, and they experience a repulsive force of F is equal to 2 into 10 to the power minus 5 Newton. Now what you do here is you bring in a third identical uncharged metallic sphere. So that sphere is identical with A and B, and you bring that third charge, that third sphere, it's uncharged, and then you bring it in contact with B. So let me name this as C here. So when you bring the sphere C, it's an uncharged metallic conductor which is identical with A and B, and when you touch it with B, now what happens here, this charge Q will redistribute itself equally between these two spheres, and then now what will happen is this Q will become Q by 2 and Q by 2 on both the spheres, and now you separate this sphere C and then place it at the midpoint of A and B. So now what you do is A is here, you have C in between, and then you have B here. Now you are supposed to find out what is the net force on C. Now A has a charge, say plus Q. Now B and C have similar charges, say plus Q by 2 and plus Q by 2. Now you know that when you bring two metallic spheres in contact, identical spheres in contact, then the charge on these two after contact will be similar. Okay. Now here we already know that before contact, so the force between A and B, when B was only Q here, so the force was F is equal to 2 into 10 to the power minus 5 Newton. So I can write that force is equal to, it is K times, it is Q1, Q2, so that is Q squared, by, if I take the distance between A and B to be R, so that is R squared, and this is 2 into 10 to the power minus 5 Newton. So this was the expression before bringing C in contact with B. Now once I bring the C in contact with B and then place that C here in between these two charges, now the distance here between these two will become, say, R by 2 and R by 2, because I was placing it at the midpoint of A and B. Now when you place it at the midpoint of A and B, now A will exert a force on C which is repulsive. So this repulsive force will act like this. So that is FCA. That is force acting on C applied by A. And B is also exerting a repulsive force on C, and that is going to act in this direction. So that is FCB. And I can see that, of course, this distance is same, and the magnitude of the charge here is greater than this magnitude, and here I have same magnitude. So FCA has to be greater than FCB. Now what is the net force on this? So the net force acting on C, F net, will be, so from this diagram it is very clear that FCA will be greater than FCB. So I need to find out what is that FCA and FCB here. Now find out FCA. So FCA is nothing but, it is K times, Q1 is Q and Q2 is Q by 2 here. So this is Q by 2 by R by 2 the whole square. So R by 2 the whole square. Now when you compare this equation here, KQ squared by R squared can be taken as F. So KQ squared by R squared can be taken as F, and the remaining terms you can see that this is divided by 2, it will become 4, it will become 2F. Okay, you can just solve this. And then FCB. So FCB is equal to, so it is K times Q by 2 whole square. It is Q1 Q2 divided by R by 2 whole square. So this gives you, it is equal to F, because it's only KQ squared by R squared. So that is F. So when you just substitute these two values here, you will get 2F minus F, which is equal to F. So therefore the net force acting on C is going to be, it is 2 into 10 to the power minus 5 Newton. It is same as that. Now in this problem, so you have two charges which are fixed in its position. So one is plus 3 microcoulomb of charge, the other one is plus 12 microcoulomb of charge, and the distance between these two charges is 0.4 meter. Now where will you place a third charge? Say the third charge is given as Q. So it is plus Q. Where will you place this third charge such that the third charge should remain in equilibrium? Now since these two charges are fixed, let me name this as charge 1 and this is charge 2. And this is your third charge. So where will you place this third charge so that it experiences zero force? When you say it remains in equilibrium, the net force acting on the third charge should become 0. Now there are several positions here. One is, say I can put the third charge in between here. I can call this as position. I can call this as 1 point, or I can also put it somewhere here, or I can put it somewhere here. Now I have three possibilities. So one is I can put it to the left of plus 3 microcoulomb, or I can put it to the right of plus 12 microcoulomb, or I can put it in between. So first you need to find out where you should place this charge so that it experiences zero force. Now let me take this position here. So let me call this as P1. Now if I place this charge, so let me call this as say Q, and this is your plus 3 microcoulomb, you have plus 12 microcoulomb. If I place it like this, now what will happen, this Q will experience a repulsive force due to plus 3, so that force will act like this. So I'll write it as F31. So this is my third charge and it experiences a force due to the first charge. And plus 12 will also repel this with a force, so that will also repel it with a force, say F32. Now if you look at this position, this charge is experiencing a net force towards this direction, so it will accelerate in that direction. It can never experience a zero force. Now similarly, if I look at this position here, so if you put the charge somewhere here, now it is close to plus 12, so it will experience a much greater repulsive force. So this is going to experience a repulsive force like that. And at the same time, if you look at plus 3 and plus Q, even these two will repel. So and that repulsive force is F31. Again you can see that these two forces act along the same direction, and this charge will accelerate in that direction, so it can never experience a zero force. Now the third possibility here, putting the charge in between these two, so somewhere here. So when I place this charge somewhere here, now this plus 3 will exert a repulsive force, we will call it as F31, and this plus 12 will also exert a repulsive force, you call it as F32. Now you can see that the idea of two forces acting on the same body in opposite direction can cancel out each other. So there is a possibility that somewhere in between these two charges, this charge can experience a zero force. Now when we talk about experiencing zero force, you need to understand from Newton's law of motion that an object will experience zero force. Suppose say I have an object, and this will experience zero force if the following conditions are satisfied. Two forces act on this body in opposite direction, so I'll call it as say F1, F2. Now these two forces must have the same magnitude, so magnitude of F1 and F2 must be same. They must act in opposite direction. So this is the first condition, the magnitude of these two forces are same. The second condition is, so F1 and F2 are opposite, so in vector symbol you will say F1 vector is equal to minus F2 vector. The third condition, you will say that the line of force of F1 and F2 has to be same, so only then it will remain in translatory equilibrium. So the line of force, must be same. And the fourth condition, both the forces must act on the same body. F1 and F2 must act on the same body. Now this is very important relation here. You need to understand, for net force to become zero, now these are the conditions. Okay, so magnitude wise these two forces has to be same, so which means F31 and F32 has to be same if the net force on Q to become zero, and these two forces should act in opposite direction, so that is also satisfied here, and the line of force must be same, so they act along the same line because these are collinear charges. I'm going to place this charge in between plus 3 and plus 12 along the line joining plus 3 and plus 12. So they are collinear, so therefore the line of force is going to be the same. And the fourth condition here, both F1 and F2, that is F31 and F32, are acting on plus Q in opposite direction. And remember, when we talk about net force 0, here clearly this F31 and F32 are not action and reaction pairs. So please do remember that, because when we talk about action and reaction pair cannot act on the same body. But you can understand that F32, which is acting on plus Q, which is applied by plus 12, and this force F23. Now these two are action and reaction pairs. They act on two different bodies. So action and reaction pair always acts on two different bodies, and they can never cancel out each other. So these are some of the points you need to understand before solving this problem. Now let's get into this problem. Now when you solve this, so I'm going to put this charge plus Q somewhere here. So these 2 points are not possible, so I cannot place this charges here. When you place it somewhere here, so it is clear that this charge 3 is going to experience a force of F31 in this direction and F32 in this direction. So when I equate these two magnitudes, I know that I can find out at what distance from plus 3 it will experience a 0 force. So we will do that first. So what is F31? So F31 has a magnitude k times Q1. It is 3 into 10 to the power minus 6 into Q2 is Q. This is your second charge, divided by, let me take this distance here. So let me take this distance as x. So therefore it is x squared. And this must be equated to F32. So F32 is nothing but, so this is k times Q1 is 12 into 10 to the power minus 6 into Q2 is again Q here, divided by, what is this remaining distance? If this total distance is 0.4 and if this is x, so this is going to be 0.4 minus x. So 0.4 minus x the whole square. Now this calculation is much more simpler. So Q will get cancelled out, K gets cancelled out, 10 power minus 6, 10 power minus 6, and this is 3, this is 12, this becomes 4. So you get, this is 1 by x squared is equal to 4 divided by 0.4 minus x the whole square. Now taking square root on both sides, it gives you 1 by x is equal to 2 divided by 0.4 minus x. So therefore it is 0.4 minus x is equal to 2x. So you get 3x is equal to 0.4, or x is equal to 0.4 by 3 meters. Now this is a very simple problem. So only thing is the conceptual part is much more important here. Now this gives you the distance. If I place this third charge at a distance of 0.4 by 3 meters from plus 3 microcoulomb, it is going to experience 0 force. Okay, now let us not stop here. Now let's also find out what will happen if I change the signs of these two charges. Now you also work out that there is going to be a very simple change in this calculation. Suppose say if I make this minus 12, so one is plus 3 and the other one is say minus 12. Now what will happen, you need to place this third charge. Now if the signs are opposite, you cannot place it in between. Why? Because if I place it in between, what will happen, if I place the charge here, this 3 will exert a repulsive force and the 12 will exert an attractive force. So it will move towards 12, it will get accelerated there. So it will never remain at rest. So now when the signs are opposite, now this is not possible. You need to put the charge either towards plus 3 or minus 12. You need to find out where you need to place that charge. Now if you place the charge towards this point, so if you put it somewhere here, plus Q, and you can see that the attractive force between minus 12 and Q is much greater than the repulsive force between 3 and Q, because here the magnitude is smaller and the distance is also larger. So the repulsive force exerted by 3 on Q will be much smaller than that attractive force. So it will never cancel out there. So this is also not possible here. Now there is only one way you need to place it. So that is, you need to place this third charge closer to the smallest charge. When we talk about smallest charge, again you need to remember which is smaller, plus 3 or minus 12. Now you need to leave out the signs here. It's only the magnitude of the charges. So signs of the charges will only determine whether the force is attractive or repulsive. So forget about the signs. So which is smaller? 3 is smaller. So now place the third charge. If the signs are opposite, place the third charge closer to the smallest charge, outside the charges. So now here this 3 will repel this with a force and say F31, and this minus 12, magnitude wise it is larger and distance is larger here, so this will attract, and there is a possibility that this is 3-2. Yeah, so there is a possibility that these two forces can cancel out each other. Now I am going to make a small change in this same calculation. So if I take this distance to be x, now what is this total distance will become? It is 0.4 plus x. So if I just change this, your whole problem is solved. So this expression is same. F31 is the same. It is k times q1 q2 by x squared. So this is your distance x, and this becomes, it is k times q1 q2 by 0.4 plus x the whole squared. So now when I change it to plus x, so you can see that now this becomes x is equal to 0.4. So now this is a very simple relation here. Okay, so now this is another problem. So there are two types of problems. So one is, if the signs of the charges are same, then how will you solve it? If you change the signs, what will happen? Now in this problem, so you have an equilateral triangle. ABC is an equilateral triangle of side length 0.1 meter, and a charge of plus 200 microcoulomb is placed at this vertex B, and a charge of minus 200 microcoulomb is placed at C, and a charge of plus 5 microcoulomb is placed at this vertex A. Now your question here is to find the net force acting on this charge placed at A due to these two charges. Now when we talk about net force, so you can see that this plus 200 microcoulomb is going to exert a repulsive force on this, so that will act like this. So I'll write this as FAB, right? So that is force acting on this charge applied by the charge placed at B. Now if you look at this force between C and A, now these two are magnitude wise same, but the sign is opposite, so this is going to attract this plus 5 microcoulomb of charge in this direction, and I'll call this as say FAC here. So maybe if you want, you can have it as F1 and F2, so nothing wrong. So I can also call this force as F1, that makes it much more easier for you. This is F2. But magnitude wise, these two forces are same. So I can write that magnitude of F1 is equal to magnitude of F2. And I can also say that the angle between F1 and F2, so this being a straight line, so this angle, I know this angle is 60 degree here because it's an equilateral triangle. So therefore this angle between F1 and F2 has to be 120 degree. So what is the resultant force acting on that? So my resultant force F of R is going to be, so I'll call it as root of, it is F1 squared plus F2 squared plus 2 F1 F2 cos theta. Okay, now this is my expression for finding out the resultant force. Now since F1 is equal to F2 magnitude wise, maybe I'll replace this F2 as F1, so you'll get it as root of, this is F1 squared plus F1 squared, that will give you this 2F1 squared plus 2 times F1 into F1, F2 can be written as F1, so that is also 2F1 squared cos of 120. Now this is 2F1 squared plus 2F1 squared cos of 120. 2F1 squared is common into 1 minus half. So cos 120 is minus half. So you can see this is, so when you take this expression, so this is root of 2F1 squared, 1 minus half is half, so 2 gets cancelled out, it is F1 squared, which will give you F1. So the resultant force is equivalent to one of the forces. So what is that force F1? So F1 is equal to, it is K times, K is 9 into 10 to the power 9, Q1 which is 200 into 10 to the power minus 6 into Q2 which is 5 into 10 to the power minus 6 divided by R squared. 0.1 squared, 0.1 can be written as 10 power minus 1, so 10 power minus 1 squared, which is 10 to the power minus 2. Now So you can just, this is also very easy for you to calculate. So this is 10 power minus 2, so this becomes 10 to the power 2 here. 10 power minus 6, 10 power minus 6 is 10 to the power minus 12. So 10 power minus 12 and 10 power 2 is going to be 10 to the power minus 10. 10 power minus 10 and 10 to the power plus 10 plus 9 here, so that will give you 10 to the power minus 1. 5 into 200 is 1000, which you can write this as 10 to the power 3. 10 power 3, 10 power minus 1, this will give you, this is 10 to the power 2, so this is 900 Newton. So my answer to this question here is the resultant force, and in which direction it is going to act. The resultant force is going to be in this direction. You can do the parallelogram law. The diagonal gives you the resultant. Sorry. Okay, now let us not stop with this here. So let's change this question now slightly. So what will happen if I change this question as both to be plus 200? Now what will happen? So if I change this to plus 200, now I know that instead of an FAC being attractive, this will become repulsive. Okay, so that will become FAC. Now the angle between F1 and F2, so this is my F2 now. And even though the magnitudes are same for both, because these two magnitudes are same, now the angle between these two becomes 60 degree. So these two are 60 degree, opposite angles are equal. So here, instead of cos 120, make it cos 60. So that becomes plus half, and this becomes root 3 F1. So therefore this is root 3 F1. So this is 3 by 2 here, so 2 gets cancelled out. This is root 3 F1. So the answer to this question will be, this is root 3 900. Hope you understood this concept. Now, just manipulating a given problem and then trying to find out all other possibilities is what we call it as interleaving concept. Interleaving is you don't just, once you find the answer, you will not leave this problem. You need to again go back to that problem, find what are all the other possibilities you can have in the same type of problem. Okay, so let's try solving few more problems. I'm giving you a lot of worksheets, so just keep trying solving problems. If you have any doubts, you can bring your doubts to our live interactive session.